So today we are going to continue from where we left off the last time. Sorry,
It's an online meeting.
my internet connection wasn't good last week. Okay, so when we started off with our journey to machine learning, we had this outline that we have been following, and we've gotten to the point where we are discussing regression. So we at this particular part, we covered supervised learning, some basic classifications, algorithms, and now we are on regression. So last week, I got the news of some of the things you covered. So what I'm going to do today is we are going to build upon that knowledge based on the fundamental concept you have gathered in there. And what we are going to do is we are going to actually build a linear regression model. And in order to start from a level where everybody can go along with us, is the fact that when we started machine learning, I remember I did this presentation, and the date is here, somewhere 24 September last year. And in the presentation, we were going through an introduction to machine learning. And then we spoke about a lot of things, but I'll quickly want to go to the point where I brought in the linear regression. And in the linear regression, just a minute. All right, so in the linear regression, we said we are going to look at a particular instance where we have some data. So in this case, we have age and weight. And then we want to train a model to learn from this data so that we can make future predictions. Because the idea I had earlier when I've explained this was maybe there's a children's ward in the University of Ghana Medical Center. So every time children go for checkups or weighing, their ages are picked and also their weight is checked. So let's assume this is an important procedure they need to perform in order to give medication and also do other things. And for some reason, the weighing scale breaks down. And for which reason, the age, it is very easy to check, but then the weighing scale is quite difficult for just someone to eyeball and assume that a baby is about 12 kg or 10 newtons. It is very difficult to do that. So if the weighing scale had broken down and somebody comes in and says that, oh, my child is about 6 weeks old, we can pick up that old data and say that, okay, most of the 6 weeks old babies or children that come here are about 20.8 newtons. So it is most likely your child is going to be of that weight. There may be some variations, but it will be around that, and we can be accurate about that. But let's say the child comes in and the child is about 12 weeks. Per the data we have here, we don't have anything precisely 12 weeks. So it will be very difficult for us to make that assumption or that initial assumption. And that's where machine learning came in. So with this machine learning, we just plotted this, okay, at least for starters. So we had a plot of age versus weight. And in this instance today, we're actually going to plot it and also plot it in Excel, look at how things are done behind the scene, and also write code to actually implement same in Python. So what we have over here is, yes, we've plotted this, and then we have, for instance, age 2, and then weight 12. So there's the age axis, that's on the y-axis, and then the x-axis is for the weight. So we see 2, 12. So 2 is about this point and 12 is about this point. So the intersection is where we are definitely going to put the dots. And then 4, 16. 4 is just under 5, and then 16 is just behind or after 15. So there's also the interception we get over here. And the rest of the data point we have over here is exactly what is plotted over here in the blue dots. And then we get a line of best fits. And I remember, and of course you also remember back in secondary school, the whole idea of this line of best fit is to draw a line that touches at least 3 of these points. Okay, so in this particular instance, we have a line that actually does a very good job in terms of it being a line of best fit because it touches about 1, 2, 3, 4, 5, and a little bit over here. So this is a very good line. Now, it turns out that yes, this graph that we have plotted, we can get a learning rule out of it. And that learning rule is what we deduce out of this line of best fits. And remember, this line should always be a straight line. So for a straight line, we can say that the equation of a straight line is given by y is equal to mx plus c. And then we know what our c is, which is our y-intercept. So clearly, you could see that the y-intercept you have over here is a negative 4.2669. So obviously, when I extend this line, it will definitely touch this y-axis, okay, at around negative something 4 points this, and that's what we have over here. And then the m we see over here definitely is the slope or the gradient. So like I said the last time, the slope is very easy to calculate, especially with a straight line. So it is a change in y over a change in x. So if you have to draw a line this way, we just pick up 2 points on the y-axis, and then we pick up 2 points on the on the x-axis, and then we look at the change. Okay, so the difference between this over the difference between this. And in this particular instance, we get a 0.4843. All right. So this is what we said was going to be the basis for we getting some learning rule, and for which reason we are going to see that this is what we call a simple linear regression. We came back to this. Now, what I'm going to do is we are actually going to look at this because I have this data over here. I'm going to share this with you. So if I'm to open this up in Excel, we're actually going to see the data, okay? And the way I plotted it, I'm going to go through that same process with you. Excuse me, please, somebody's microphone is on, so kindly mute yourself. Thank you. So what we have is definitely this data, and this is what we are going to work with. So I can highlight this data in Excel. And like I said, I'm going to share this with you so at least you can practice on your own. And then what we need is, okay, under the insect tab, okay, under charts, I can pick up something from the scatter. Okay, so this scatter plot is what I need. So I'll select this one. And this scatter plot is basically plotting what I have in terms of the data showing up over here. Let me try and see if I can expand this a little bit. All right. So this is what I have. And I believe, yeah, so I have weight, okay, on the on the x-axis because, and I also have age on the y-axis because clearly the highest value I have for age over here is 20, and the highest scale I have over here is 25, so at least it will cater for 20. And then over here, the highest weight I have is 47, and then I have about 50 over. So at least that's just an indication to show me where the axes are falling. Now, what we can do is, in order to get that line of best fits, okay, we just click on this plus button over here to add more features. And you see that there's a trend line over here. So when I click on this to check this, by default, it is going to give me the linear regression trend line, or at least that's how they call it over here. Good. Now, I can further click on this to get more trend lines. So over here, you see that the default is a linear. Now, depending on the data, and that's why visualization in this space is very important. Once you're able to visualize your data, you can actually project, okay? So if we had wanted, for instance, maybe an exponential regression, okay? If we had wanted, for instance, an exponential regression, we're going to have something like this. And you know how an exponential curve is going to be drawn. But you see, at the end of the day, that exponential curve is not just going to be like any exponential curve we've seen, but then it's going to be drawn particularly based on the data points we have over here. So in this case, yes, the rule still remains that it should touch at least 3 points, and that's what it is trying to do over here. So even though it is not linear, it is in that parabola shape, but at least it is trying as much as it can to touch at least 3 points and also to have that exponential shape. But sorry, but clearly you can see that the exponential one is not going to help us, so we are going to stick with the linear. And let me just uncheck this one. Yeah, so this is a linear. And then what I also want to show you is if you go to more options over here, you have, I mean, this one. So if you want to do something polynomial and any other thing, you see them over here. But then when you scroll a little bit down, we also want to display the equation on the chart. So I'll check this box. And then we have the equation of the line over here. And that's essentially what is giving us, for instance, our y-intercept is what we see over here, the negative 4 points, approximately 3. And then the slope is what we also see over here as a 0.5, sorry, a 0.48 approximately. So this is what you have. And then what, sorry, what I'm going to do next is actually to now, okay, we can really do this in Excel, okay? But then why do we want to do this in Python? Is it not too much work? Because over here, we just clicked on some few buttons and then we have this. At least we have this equation of a line, and we know that this is the basis for which we are going to make predictions one way or the other. So for instance, if somebody comes and we want to calculate the weight, all that we need is the X, which is the age. So given the age, we can do that change of subject over here or plug in the value and then we get the weight. So that's very simple. But then there are some inherent limitations with Excel. Okay. And let me just show you this because I actually go to the official Microsoft website and they are telling us about Excel specifications and limits. Now, when you go down just about here, it tells you the total number of rows and columns on a worksheet. So there's a limit. It's about a little over 1 million number of rows and about 16,800 and 384 columns. Now, maybe for some data that you may be working with, 1 million may be more than enough in terms of what Excel gives you. But the whole idea of machine learning is the bigger the data size, the better for us. So even if you have 10 million instances of data, that's actually going to make your machine learning model learn very well. So there are some instances we may we may not necessarily need Excel to help us. So that's number one, because of the limitation on the number of instances we can have. Now, the second limitation is definitely what we see over here. Now, the big question is, okay, now I have this. Maybe I want to deploy it in a web application, a mobile application, or any other application. And the big question is, how do I get this extracted from Excel and deploy it? So that one too is a very complicated situation. I haven't come across any solution. But then even if there is, okay, you can imagine how complex that solution is going to be. But then in the case of we using Python, we can simply save that model and also load it or deploy it in any other place that we want. So we are actually going to go through that process of now developing this. So we are actually going to develop this based on this data set, at least this small data set, to actually cover the principle or at least the fundamental concept of the linear regression model. And then later on, we are going to look at a more complex data set, which is going to also give us some perspective and how we analyze data one way or the other. Just a minute, I'm coming. Okay, so I'm back. So what I'm going to do is I'm going to come back here, just open my Jupyter Notebook environment over here and start working right away. All right. So I'm going to open a new notebook and we are going to work our way through. So I'll need some few libraries. These libraries are libraries we've been using over and over again. So I'm going to import NumPy as NP, and then I'm going to import matplot. Okay, so from matplotlib import pyplot as plt. Then we also want the linear regression algorithm model, which is already written for us in scikit-learn. So remember, scikit-learn is our go-to place where we get a lot of these algorithms models from. So I'm going to say from sklearn dot linear underscore model. I'd want to import the linear regression, and I think the spelling should be okay. Then finally, we want to look at some performance. Okay, we want to check this time around, not accuracy, but then how well our model is performing one way or the other. So I'm going to say from sklearn.metrics. Remember, when we're dealing with, for instance, the classification, we're looking at the classification reports, confusion metrics, and all those things, and even accuracy. This time around, we can use accuracy, and I'm going to explain that very soon when we actually get to the point where we are analyzing the performance of our model. So over here, we are going to do, or we are going to use the mean squared error performance metric. We are going to look at the R squared as well. So it is called R square this way. And I believe these ones are good enough. So sorry, from import. So let's run it. And then maths plot, okay. So there's an L over here. Oh, what is happening? Pyplot, okay. Okay, so this one is looking good. Now our data set is here. This is an Excel data set inside of, I believe the file extension is CSV. Okay, no, this is Microsoft. Okay, this is an Excel. Okay, now what I want to do is we can actually get this data. Okay, so what I'm going to do is let me just put in a comment over here, and then I'm going to say the weight. The weight is going to be equal to np dot array, and then what I want is I'll just type in the numbers because they are few. Okay, so let me see if I can copy this, Control C, and then bring them here. Okay, and let me just put in the comments over here to make them work. Okay, so this is going to be the weight, and then let's look at the age. So the age is also going to be np dot array, and I'm going to have this, and let me also come in here and copy this. So I'll do a Control C, come in here, and then also make sure that everything is working. Okay, so we have our data, and then what I want to do is let's have a preview of the data. Okay, and there's something I would want to do over here, but I would want to tell you exactly why we need to do that. All right, so we have, for instance, the weight showing up this way. Clearly, without even checking, we can tell that this is just a 1D array, okay? And this is also a 1D array by just the number of opening brackets that we have. that trick I showed you some time ago. So this are weights. But then the way the data set is modeled, okay, it is modeled in such a way that this instance or this row, okay, so when I say instance, it is just another way of saying row. Now, the rows match up onto each other, okay? So for instance, this 12 we have over here is matching up with its corresponding pair, which is the age 2. This 16 we have over here is also matching up with its corresponding pair. And this 18.5 over here is also matching up with its corresponding pair. But then the way we have it this way is not making it look like it, okay? For instance, this is now behaving as one thing on one row, but we want to have it each one on its own row. And one of the ways we can go about this is now to reshape this, okay? So now let me do a dot reshape over here, and we are going to see the difference. So I'm going to do a negative 1, 1 over here. So I run this, and now see how width looks like. So now you can see that this 12 is more or less separated from this 16. And just by reshaping, we have also created the fact that this is now becoming a 2D array. So it is not precisely the same as it was when it was just a 1D array. So that at the end of the day, we can see that this instance is matching up with this at the Y end, okay? And this is also matching up with this at the other end. This is also matching up with this at the other end. So that's just something I just want to draw your attention to. So we have the data. The next thing to do is something we've done over and over and over again. We just creating a variable called model. So our model is going to be equal to, and we just bring in the linear regression algorithm model that we have imported from scikit-learn over here. Now, if you remember, there was a kind of a pattern, okay, in that we just instantiate it this way. And then the next thing for us to do is to now to do a model.fit. We bring in the data, and then we can train the model after fitting. So I'm going to do model.fit. And then what do I want to fit? I want to fit the weight and then the age, just as I have them showing up over here. So I'll run this, and then the training is complete. Okay, clearly there's a very small data set, so in a matter of seconds, everything is done. So now that I have this model, there are some few things I would want us to see even before we go through the analysis of it, because it turns out that when we are dealing with machine learning model development using Python, a lot of the heavy lifting, a lot of the heavy work is done behind the scene. We don't get to see them, okay? But then this is what I want us to do. Now, if I'm to come here, model dot, and I bring in tab, I believe they should come. Okay, very good. You can see that I have a number of things I have over here, which is inside of the model that was created for me. And the first one I have over here is the coefficient, okay, which is definitely going to be, when I run this, we see that we have a 0.842 whatever, okay. Now this is going to be the, how do you call it? The, how do you, the slope, very good. This is going to be the slope. So you see that over here, we get to see the slope behind the scene. When we are using Python, we don't necessarily get to see the slope, but then it is calculated for us. And over here, doing it in Excel, we get a 0.4843. Here too, we get a 0.484. So there's an approximation over there to make this 43, but then you get the actual number showing up over here. If you have time, you can actually plot this on a graph sheet and actually do the calculation manually yourself. All right. Now, so these are some of the parameters that's going to inform or make our model get the line of best fit. So those things are calculated as soon as that model is fitted with the data set or that training is done. Now, the other thing we also want to see is, of course, the y-intercept. So now when I do model dots, and I just want to have the y-intercept, and that's what I have over here. So this is the intercept underscore, okay? So when I run this one too, you see that I get a negative 4.2669, and there are some other numbers over here. So a negative 4.266. And if you are to go back to Excel, we get to see that, yes, indeed, we are getting a negative 4.2669. So clearly you could see that even though we don't see them, okay, it is there. It is we only see them when we ask to see them. But then at the end of the day, this is what is going to be the engine behind whatever model that we have created. But then this is going to be because of the data set we presented it. If we present a new or a different data set with different parameters, different numbers, then obviously the slope may be different. So that slope will be calculated and the number could be different, and also the y-intercept could be different. So that's just something we should know, that even though we haven't seen it, but then it is calculated behind the scene for us. So now that we have this, let's actually see this. So we have created something, okay? Now let's do a prediction. It is only when we do a prediction that we will be able to compare what we have predicted with what the actual data is. All right. So now let's see this. Now, if I'm to do model.predict, and over here, once again, this is a very small data set. So we weren't able to even split the data into a training pattern, a testing pattern, all those things. Like I said, this is just for us to get that general understanding. We are going to have other data set that's going to give us a more complex view of how things are done. So when we do model.predict, what I want to do is I just want to pass in the weight, okay? I just want to pass in the weight to do the predictions for us. And now let me call this the predicted underscore age. So now let's have a preview of the predicted age. So these are the predicted ages, okay? And let's have a view of the actual age, because indeed this is the actual age. Okay, so you can see that clearly there are some variations over here. In the first instance, the predicted age was about 1.54, okay? And then we are getting, or the actual thing was a 2. In the second instance, the predicted age was a 3.48, but then the actual was a 4. In the third instance, the predicted age was a 4.6, but the actual was 5. Over here, we have the predicted showing up as 5.8, but then the actual was 6. In this particular instance, the predicted was a 6.9 and the actual was 7. This one was pretty close. And it goes on and on and on to the last one, where we have a predicted of 18.6, but then the actual was this. I think the closest amongst them was probably maybe the last but one, okay, where we get a 5.10 predicted or prediction, and the actual was a 15. So at least you get the point. Some learning has been done, some prediction has been done. But clearly you could see that the way this prediction and the way we are comparing it with the actual thing is that over here, we would want to calculate or measure the variance or the magnitude of error. The magnitude of error. And that's what brings us to this one, the mean squared error and also the R-squared error. Now, the way we measure this error and why we use the mean square error and also the R-square error, it's like that. You see, it's almost like how we measure distance, okay? And distance is distance. And distance, in its realistic sense, we cannot have a negative distance. And that's why most of calculations, when we are trying to calculate for distance, or maybe there's this popular one, I've forgotten. Yeah, when we are trying to calculate for distance and stuff like that, we always try to use, let's say, let's say D1 minus D2 all squared. So that at the end of the day, if we get a -2, we are going to square it to actually get that positive value one way or the other. And that's what we are doing over here. So we are going to use the mean squared error and also the R-squared error to get some values to see how our model performed. So in order to do that, the mean squared error is now going to be equal to the function we have imported over here. And then what then do we pass? We pass in the age, which is the actual, okay? The actual age, and then the predicted age. the predicted age showing up this way. And then we run it, and then some value has been calculated. I'm going to show you the formula, the mathematical formula behind this. And so we get to see that this is a 0.56 in terms of the mean squared error. Now the mean squared error, the formula is, let me just see if I can use the whiteboard. What is this? Good. So for the mean squared error, it is going to be a summation starting from starting from 1, okay, and ending at n. That's the number of instances that we have. Then we are going to have a 1 divided by n over here, and it is going to be the actual, okay, so let's say I call this y minus the predicted, which most of the time you are going to see it like y hatch this way, then we are squaring it this way. So it is a summation of this, okay, all squared, and then we half it, or we divide it by the total number of instances that we had. So let's try and see if we can do this manually and see if we can get this value as it is showing up over here. So let me just go back to this. So there's a simple way of doing this, but then let's just look at this. So it is going to be 2, okay, minus this, okay, and remember it's a summation, so we are adding. So 2 minus this plus 4 minus this plus 5 minus this plus so on and so forth. But we can look at it in a very simplistic way, in that if I'm to do, let's say, age minus the predicted age, minus the predicted age, we get this over here. Okay, so this is doing a pairwise subtraction of everything we see over there. All right, now let's just confirm from one of these so that at least we know that everything is looking good. So let's say we have 2 minus what we see over here, and let's compare if we actually get this value so that we can be rest assured that maybe the others are correct. So we get a 0.45574. Okay, that's exactly what we have over here. Let's do at least randomly for the last one and see. So the last one is going to be 20. So let me just add 0 over here. 20 minus this 18 points, whatever thing we see over here. And over here, we are getting the 1.36118. And that's exactly what we have over here. All right. So this one is looking good. Now, let's, so we have the, how do you call it? The summit, the subtractions. So now let's square this, okay? So what I can do is, I just want to have this, see if that's maybe x is equal to this, okay? Now, x squared is going to be x times x. So we have this, okay, everything has been squared. Now that everything has been squared, we need to do the summation. So we need to sum everything up. So summing everything up, we can do np.sum, and we pass in x is equal to this, okay? So np.sum, and then we pass in x over here. And then we are getting this as we have it over here. But then remember, it is all divided by the number of instances. So now let's go and count the number of instances. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So even without this, definitely you see that we are dividing by 10. So the decimal point will shift 1 there. Okay. And that's exactly what we see over here in terms of the value for the mean squared error. So let's do it actually. So let's say y is equal to this, and then now we do y divided by 10, and that's precisely what we get, okay, without doing the manual calculation, but you get the point. Now the whole idea of why we need this is we want to calculate and see the overall error in terms of the magnitude of error, the variance, okay? Now, this error we see over here, if you are to look at it in terms of percentage, is about 56%. Okay. If our mean squared error is about 56%, then we definitely have to do something about the model because that is too big. What it can also translate to mean is that about 56% of the time we may get our prediction wrong, or the variance is going to be too wide. Okay, over here, the key thing is the variance. Okay, over here, the key thing is the variance. So over here, that's this 56% error, margin of error, basically is telling us that, well, there's a 50, on average, there's about a 56 variance in terms of what is predicted and what the actual is. Okay, and we can actually do an eyeballing of this, at least with this one. Okay, if we are to look at the percentages, okay, this is a predicted, this is the actual. This is about, if I'm not mistaken, what percentage of, let's say, a 1.5 is 2. Okay, those are the things you should be thinking about. What percentage of a 3.5 approximately is 4? What percentage of a 4 points? And everything has been summed together. So this, at least for this one, is not looking too good. But then it is the data that we have, and clearly you can see that this data is very small. So there's definitely going to be a margin of this error. Now let's look at the R squared metric and see how that one can also help us. So I'm cleaning this up over here. So for the R squared, once again, I'm going to do R squared. And please, just a minute, I'm coming. Hello. Yeah. Good evening. Okay. Please, can you hear me? Hello.
Yes, please.
Okay. Sorry. I'm using my phone for my internet connection, and someone called, so definitely it's cut the line. So now let's look at the R squared error. And over here too, once again, this R squared has been imported over here. So it's very simple. We pick it up this way. And then once again, we look out for the values that we need. So we need age. And then also, we also need the predicted age. So I'll pick this up as well. And then when we run this and do a printing of the R squared error, clearly you could see that this is also not looking too good. Okay. The smaller the errors for us, the better for us. But at least with this data set, there's little we can do to even improve performance. So let's just go straight to some of the things that I would want to show, and we are going to come back to building a bigger model, or let's say a model with a bigger data set, and then we can see how things will look like. Now, what I want to do next is actually to get a plot, okay, that looks like this, okay, based on the data that we have, and also see how we can also visualize things and also get our regression line and make things look better. Because if you are not quite experienced with this and you are seeing these numbers, maybe things may not be too clear. And if you are going to do a presentation of a model, you don't want to be showing too much numbers. If there are some graphics, it makes your explanations even simpler. So what I'm going to do is, first of all, I'm going to do plt.scatter. Okay, I want to have a scatter plot, and the parameters I want is width and then the age. So let me run this and see. Okay, so basically this is the original width and age. Okay, just as how do you call it? Excel will give us, okay, the original width and age for the scatter plot. So we have this, and let me just bring in a few things to make things look a little bit better. So I'll choose a color myself. And let me say for color, I'll choose black. And then I'll have a label for myself as well. So for the label, I'll call this actual data. So I have this, and let me just come in here, plt.show. Okay. All right. Now there are some things I want to show. For instance, the regression line. So for the regression line, that one can be plt.plot. And what I want is the weight and the predicted age, because the weight is more or less going to be there, but then the predicted age is what is going to show me exactly where the I'm doing a comma over here, dot. So I'll do the predicted underscore age over here. And let me just see how this one looks. Okay. So this is the line that we see. But then if we are to, for instance, do a scatter over here, this is also going to show, at least with the plotting. Is that okay? Because behind the scene, okay, basically this is what we are plotting. Behind the scene, we've plotted first. The first plot we have over is the actual weight and the actual age from the original data set. And also behind the scene, we have the actual weight and some predicted ages that we want to plot alongside to actually see the variance. So clearly you can see that this one, the predicted is the one. Okay, let me give this one to another color so that it becomes obvious. So let's put red over here. So the predicted is red and the actual is a black. Okay. So you see that over here, the actual was this black and the predicted was this. So this variance is what we have been calculating as a mean squared error. Is that okay? And in some instances, we don't want it plotted this way. We just want it as a line. Okay. So that we can see it as a regression line. So that's why we are doing a plt.plot, so that that one comes in as a line. So there's a line that we have as a regression line. And then what I want to do over here is I also want to give it a label. And then for the label, I'm going to call this the regression line. All right. Now there are some few things I would want to have over here. I'd want to do a plt.legend so that the legend will show in here. So anybody who sees this is like, okay, the black is the actual data and the red we are seeing is the regression line. So everything makes sense, especially with this plot. And then let's give it a title and the X label and the Y label, and we can actually have a proper look at this. So plt.title, and then what I'm going to call this is, I'm going to say a linear regression model, and then the plt.x label, and then this is going to be, the X is going to be for the weight, and then plt.y label, sorry, and that's going to be for the age. Okay, so now everything looks good in terms of what we actually want to show. And then I think this is a better representation of the model that we have built, which is not too different from what we have over here in Excel. Okay, we can do a number of things, bring the equation line and other things to make things look good. But once again, once we have this, and especially if there's a report that you are writing, this one looks very visual. You don't have a lot of numbers over here, but anybody who sees this, and based on the explanations you are going to give and the legends you have over here, everything makes or everything is clear. Now, the interesting thing is, remember what I said in the instance where, let's say, somebody comes into the hospital and that person, that person wants to make some prediction. Okay, let's say if that person is okay, so age is going to be our friend over here. So let's say if that person is about 11 years old, we'd want to calculate the weight. Okay, so what we can do is, now if I'm to do model dot predict and passing, I believe this should be, let me see 11 this way, if this one is going to work. Okay, so this one is not working. Let me do np.array and make this an array. Okay. It is still looking at it. Just a minute. It says I need to reshape. Okay. So once again, the reshape thing we saw dot reshape, and then let's do a -1, 1 over here. All right. So that's what we see over here. That's this is giving us a 1.05. This is not what I expect. But then let me see what this one is actually looking like, because okay. I don't expect to see a 1.05. Perhaps maybe something is not right somewhere. Maybe the way I've presented it. Let me do 100 over here and see. So 100 is giving me a 44.14. Okay, so 100. No, it's still not making sense, because at the end of the day, the formula we use over here, which is the y is equal to mx plus c, is more or less the fundamental principle for any prediction that will be coming in. And we know that in this particular instance, our coefficient, which is the slope, is a 0 point. Let me write this down over here. This is a 0.48. So 0.48, and this y-intercept is a -4.2. Let's say 27. So with this in mind, if I am plugging in a y, okay. If I'm plugging in a y, no, if I'm plugging in an x, okay, if I'm plugging in an x for the corresponding, okay, so the initial 11 was something which was lower here, so it was pointing to a 1 point something, if you could see that. So if this is 11, it will point, 11 is somewhere here, so as and when 11 touches this line, it will point to a 1 point something, and probably that's what we saw for the 1.05. Okay, but then let's say if it is a 27, okay, a 27 will be somewhere here. So if I'm to draw this line, let's try and draw this line. If this is about 25, this would be 26, 27, 28, and then 29. Okay, so these are 26. So these are 27. So let me just get some kind of something to represent something. Okay, so we expect something around 8 point something. Okay, so let's try this one and see. So if I put in 27 over here, we expect to see an 8 point something, at least something within the region of 8. Very good. And that's exactly what we see over here, the 8.80 in terms of our predicted age. All right. And if we are to actually manually calculate it by hand, let's also do that using this formula. Okay. So our x is 27. So if I'm to come in here and do our slope is a 0.48 approximately. Okay, multiplying the 27, which is the value we want to make a prediction out of, 27 plus because this is negative, let's just do it right away, approximately 27. So because of board mass, let me just put this out over here. Okay. And then we get, because there's been some approximations over here with these values, okay, but then you get the point. We are getting something which is closer to what was actually predicted. All right. If we want to be 100% sure, and let's also be 100% sure over here. This is our coefficients, Control C, multiplying 27 minus the y-intercept. Let's bring that one over here. Good. Okay. We get exactly what was predicted. Okay. So this is just for precision's sake and to make sure that everything is looking good. So that's exactly what we have over in terms of the prediction. And everything, like I said, is centered around the equation of a straight line. And we've seen how we could have done it with Excel, but then Excel has limitations. The first of which is that there's a limitation on the number of instances. So if our data set is very huge, okay, let's say we want to draw a linear regression and predict maybe voting patterns in Ghana. The number of people who voted in the last election were about 50 million, okay, or maybe 30 million thereabouts. So that 30 million, Excel is not going to help us get all the number of instances and where they voted and how they voted. So in that particular instance, then Python is going to be our best bet. Now, when we are done with Python, we can save this model and then deploy it in some application somewhere for people to use, which is something we are going to discuss hopefully in the in this section, okay, where we are going to deal with web apps with TensorFlow, web ML overview, creating a web application for ML, integrating our machine learning models into some web applications and model tracking and stuff like that. So by the time we get to this point, at least we'd have built some other models going back to neural networks. This time we're going to look at deep neural networks. And then when we get to this level, at least everything is going to look good. And eventually when we get here, this is where we are going to use images, okay? We are going to learn how we build models for image recognition and stuff like that, which I believe some of the project work you'll be working on will deal with that as well. So at least this will be a good place for you to learn some of the fundamental concepts and also try and build some models even before you actually deal with your proper projects. All right. Please, at this point, any questions, because we are almost done. Please, any questions? If anyone is talking, probably you have muted yourself, so I cannot hear you. Are there any questions? Okay. So if there are no questions, okay, please, you can proceed. I've seen a hand up.
This about the model creation.
Yes.
I know the training model. Sorry.
Terry,
When
please,
you
can you
fitted
speak up a
the
little bit? Please, can you speak up a little bit?
okay. Hello, please, is it better now?
Yeah, it's better now.
Okay. So please, I was asking about the model fitted. When you fitted the model with the data,
Mm-hmm.
how did it distinguish between the two? And then you see when you were trying to predict a value, you inputted a single value, but then what you your intention was to find the age. So how did it know that this is the weight? I mean, what you
Oh,
inputted was
okay.
the weight.
Okay. Okay. All right. So let me answer the last question. The first question, I didn't get it too well. But then the last question is based on the fact that, once again, and that's why I had to write the formula, because just to reference, y is equal to mx, okay, plus c. So at the end of the day, based on this fundamental mathematical principle, it is the y that we are going to predict. And that y is what we have on our y-axis. So if we want to predict something, it is a it is a weight that we need to put in order to get the weight. Now, one of the things you also know is something which is very fundamental to this, and is the point that based on the way we have structured this, okay, based on the way we have structured this, what we have ended up doing is the weight is now what we call the feature or the independent variable, and then the age then becomes the target, which is the dependent variable. So I think when we build other models, I'm going to come back to this and explain this very well, but this is the initial thing. Now the point is the fact that this is on the y-axis and we are predicting y, that is where or why we needed to put in something for x, and that's what we see over here. This on the x-axis, weight is on the x-axis. So we put in the weight, we can draw that line to get the y. Please, I hope you are answered in a way. Yeah, hello. Yes, sir. Oh, you remember. Hello, please, can you hear me?
Hello.
Yes, hello. Can you hear me?
Yeah, I can hear you now.
Sorry.
Couldn't hear.
My line dropped. Someone was calling me, and so Sheriff, do you know? So I think the first question has been answered, or the second question has been answered, right?
Yes, the second question.
So let's go to the first question.
Yes. So the first question was,
Okay.
when you fitted the data,
Mhm.
how did it differentiate it that this was the feature and this the label?
Oh, okay. So that one is based on how we place these parameters over here. Okay, so at the end of the day, you see that it is expecting an x first before a y, basically. Okay, based on how things are structured over here. So it pretty much depends on how you are working and what you want to predict at the end of the day. So it is going to see this as the x. The first one you bring in is going to see it as the x, and the next one you bring in is going to see it as a y. Please, are we all clear on this?
Yes, please. Thank
All
you
right.
so much.
You are welcome, my brother. So please, are there any questions? Because I have to catch up on something. Somebody has been calling me to do something. Okay, so if there are no questions, we can end it for now. At least we've seen some few things. I'll share the video with you and then you practice. By Friday, we'll deal with some different or more complex data sets in order to get our hands busy on some of these things. Okay, so thank you very much, and we meet God willing next week. Hey, on Friday, sorry. Hey, today is Friday, so next week. Sorry. Okay, bye-bye.